Okay, so now we're going to finish the actual lecture notes on lesson 13. And we have 4 questions, and we have a couple of like multiple ones in there. So on some of the ones, I may give y'all a chance to do it yourself, and then make sure that on Friday that I give y'all a chance to do some participation points since I'm not there today. So starting off, the first question says determine the oxidation states of the elements in the following compounds. So we have to kind of keep in mind our rules that we said right here. And then the other thing we have to remember is that each of these compounds as a whole is neutral, meaning that there's no charge. If I look at sodium iodide, there's no charge up here in this upper right hand corner. So that means that the compound is neutral overall. So whatever the charge on sodium and whatever the charge on iodine is, they must add up to equal 0. Okay, so the nice thing about sodium and iodine on this first example is that sodium is a group 1A and iodine is a halogen. So we know from our rules that the charges must be 1 plus and 1 minus. And so we can see that 1 plus 1 minus equals 0. So what I said earlier about neutral is still true. Now the next one is gadolinium and chloride. So we need to look at the periodic table and look at where gadolinium is, and then think about where chloride is to determine do any of our rules apply from before. Okay, so we have gadolinium and chloride. So we know that chloride must be 1 minus because of our rule about the halogens. So even if we're not sure about the gadolinium, we could always look at the chloride. Stop. Sorry guys. The chloride, we made it through the whole first video without any fighting, and now this is what life is really like. We can use what we know about the chloride. Okay, so if I know that I need this rule up here to be true about it being neutral, and I know I have 3 1 minus charges, okay, for the chloride, I can solve this like algebra. X minus 3 equals 0 because 3 times negative 1 is negative 3. And then I can rearrange it by adding 3 to both sides. And what I get is that in order for this to cancel out, the gadolinium must be 3 plus. Okay, so I didn't have to know anything about its place on the periodic table because I knew the rule about one of them. Okay, and so essentially oxidation states we can treat a lot like our knowledge of algebra. Okay, so the next one is lithium nitrate. So we actually have 3 elements in this one, but we know that this is a metal plus a polyatomic. Okay, so we know that we're going to have 3 elements to determine its oxidation state, but we do know that the overall charge of lithium nitrate must be 0. So our rule says that all group 1A's are 1 plus, and oxygen most of the time tends to be 2 minus. And so what we don't know is what nitrogen is. Now, nitrogen on the periodic table is 3 minus, but we can't have 2 negative and 3 negative equal out with the 1 positive. Okay, so in this case, nitrogen is going to adopt a oxidation state other than what it normally would have on the periodic table. So I'm going to set up a little algebra formula. I'm going to read left to right. My lithium is 1 plus. My nitrogen is what we don't know because it can't be another negative charge in order for all of this to cancel out. And I have 3 negative 2's. And I get the 3 from the subscript, just like I did before. Okay? So now I have a formula that I can say equals 0 because lithium nitrate is neutral, does not have an overall charge. And I know that lithium 1 plus and oxygen are 2 minus, and so now I'm going to solve. So in this case, I'm going to have 1 plus x minus 6 equals 0, which will reduce down to this because the positive 1 and the negative 6 will leave me with a negative 5. Add 5 to both sides, and what this tells me is that x must be positive 5 in order for lithium nitrate to be a neutral compound. Okay, so those are my oxidation states. Alright, the next one is H2SE. So I'm going to have only 2 elements in this one. And I know that hydrogen tends to be positive 1. I also can tell that it's probably positive because it's written first in my formula, which means that it tends to be my cation. So I'm going to write 2 times plus 1. And what I'm trying to determine is the charge on this selenide, right? That's my anion. Okay, so plus x equals 0. So you can see that it's going to be x plus 2 equals 0. Subtract 2 to both sides. Gives me a negative 2. Okay, so that's probably not much of a surprise about its charge, simply because it is in group 6A with sulfur, and that is the charge of 6A ions. However, it never hurts to just double check to make sure that that rule is still true, because group 6A elements were not part of our rules that we stated before. Okay, so we can't assume that that's always going to be the case in covalent compounds. Alright, I'm going to leave these two for CP points on Friday. Okay? So when I come back, these two will be an opportunity for you to practice oxidation state calculations in class for CP points. The last one is very similar to the first one we did. Hydrogen, much like sodium, tends to have a plus 1 charge. Fluoride, much like iodide, tends to have a 1 minus charge, has more to do with their placement on the periodic table. And so in this case, 1 plus 1 minus equals 0, which we know to be correct because it was before. So those are the oxidation states of the hydrogen and the fluorine in this compound. Alright, so now we're going to, I pulled some questions from the back of your chapter. There are suggested problems if you ever want extra practice in practicing any of this stuff. A lot of the times I've pulled them directly from your textbook, just because they're written in the same language as what you might be reading and how I'm thinking of formatting the questions. And so these are at the end of chapter 4, and it's question 14, and it's A through D. So in this case, the question gives you a balanced chemical equation, and then it's asking you to determine the reaction type. Okay, so I'm going to write these in. Man, I cannot remember to put potassium in. Okay. And some of these types we will have talked about last time. And some of these we just have given a name this time. So I'm going to write all the equations in. go. Yes, just go. Okay, go. Okay, I'm letting my kid have a milkshake at about 7:52 in the morning, so hopefully he will let me finish the rest of this lecture. Okay, so in the first one we have water as a vapor. It's a gas reacting with solid carbon to form carbon monoxide, which is a gas, plus H2, which is also a gas. Okay, and then in the second one we have 2 potassium chlorates as a solid, reacting to form 2 potassium chloride solids, plus 3 oxygen, which is in the gas form of a gas. Then we have aluminum hydroxide, aqueous, plus 3 HCl, aqueous, yielding aluminum chloride, which is also aqueous, plus 3 waters, and then this one is a liquid. Okay, so I know my L may not look like a liquid, but it is. And then the last one is lead nitrate, aqueous, reacting with sulfuric acid, aqueous, to form lead sulfate solid and nitric acid, aqueous. Okay, so they're balanced. I think in the question it even says specifically that they're balanced, but remember when we started talking about balancing chemical equations, I told y'all that if it doesn't specifically say it's balanced, you should always assume that it's not. Don't assume that every equation you get from now on is balanced, because now that you have that skill in your toolbox, I expect that that's one of the first things you should be thinking about is it balanced? All right, so the question wants us to determine what type of reaction, classifying it. It gives you a couple of options on how to classify them. So we've talked about single, double displacement, combination or synthesis, and decomposition so far. And then in this particular chapter, now we're talking about precipitation, acid-base, and redox reactions. So those are the 3 that we added on today. And so we're looking at really which of the 7, in addition, combustion is a subtype of redox, are we looking at. So in this case, in the first one, we have water plus carbon yields carbon monoxide and hydrogen gas. And so this particular one, if you can look at it this way, okay, so I'm just giving them generic letters to kind of look at what's happening. And if I write it this way, this may look more familiar to you as a single displacement, because the element that has, or the compound if it is, the element that has C written above it is displacing A on the first reactant, which is my hydrogen gas. And then A is by itself as a product, and C and B have now combined to form a new compound. So it's single displacement. Sometimes, especially in sapling, you'll see this as single replacement, and it means the same thing. We're talking about one reactant coming in and displacing something in the other reactant to form two new products. All right, so the second one, we're starting with one reactant, and we're forming 2 new products. And so if we think about what we see happening here, if I write them with the A yielding the B plus the C, this may remind you or make you think of the decomposition that we saw last time. Okay, now remember, so what if I took the reaction, and I'm leaving off the phase states just for time, and I reversed it, and I made my products my reactants and my reactants my products, so flip-flopped it. This would be combination or synthesis. Okay, so decomposition and combination or synthesis, they are reverses of each other. Okay, one's happening in the forward, the other one's happening in the reverse. All right, so now we're getting down to our last 2, and looking at the third one, I might be tempted to say that maybe this is a double displacement reaction, just because I know from that last lecture that we have A and B plus C and D. Oops, sorry guys. Haven't used green yet. Okay, so I know I have A and B, C and D, and that's becoming A and D and C and B. Okay. However, if we think back at the very beginning of this lecture, we defined acids and bases. And one of the things about the bases was the presence of this OH group and the proton in the front. And so now if I go back down here and I look, I can see very clearly that this is a strong acid, and then this is not one of my strong bases, but it is basic because of the presence of the OH. So it's a weak base, but it's still a base. Okay, so this in particular is not a double displacement reaction, but it is an acid base reaction. Okay, so anytime you see an OH and then the hydrogen, or you can identify a strong acid, strong base, or weak acid, weak base, then we're going to call it an acid-base reaction. So on that note, back up here, if it is not strong acid, strong base, it is a weak acid or weak base. Okay, so you need to know the 6 strong acids and the rules for strong bases, because if it's not strong, it's weak, and there's a lot more strong weak acids and bases than there are strong acids and bases. So it'll benefit you to know the rules about identifying strong and strong acids and bases, because everything else will fall under the category of weak. And we'll get into talking about what acid-base chemistry is more so in the second semester. But the ACS final is going to ask you which of the following is a strong acid base. And so knowing them will help you now, but it'll also help you in the next class. All right, so last one for this particular question. Let's pick a different color. So we have lead nitrate reacting with sulfuric acid. So I know that this is a strong acid, okay? And it's going to make lead, sulfate, and nitric acid. So I might be tempted to think, okay, well, the last one said acid base because it was a strong acid and there was an OH. But lead nitrate is not a base. Okay, so looking at this, I know that this can't be an acid-base reaction, because an acid-base reaction requires the presence of an acid and a base. And I know that lead nitrate is not a base because it's not an OH group. Okay, and the only exception that we typically see to having an OH group within a basic compound is ammonia. Ammonia is just NH3, okay? But it is a weak base. And it's one of the rare exceptions to the fact that it doesn't have an OH group in it. And but there is a form of ammonia called ammonium hydroxide. And when we buy ammonia as a lab, we typically buy ammonium hydroxide. And then when you open it, it very quickly is ammonia, which is what we need in the lab. Okay. So I know that this is not acid-base, but I can see the trend of A plus B, AB plus CD making ADCB. And so this is a double displacement or replacement reaction. Okay. So very typical multiple choice type questions on the ACS final. Therefore, you'll definitely see some on your exam 2 coming up. Okay, so I would recommend this ABC patterning, really great for note cards. just because if you can identify how these are moving around, it'll help you to make the correct reaction identification. Okay, so a lot of it's just patterns. All right, so we are going to complete and balance the following acid-base equations, but I'm going to only do the first one, and then these will be 2 CP opportunities on Friday, okay? So that y'all can have, it should be about 4 up to this point. Okay, so we have to complete and balance. So my first one, fortunately, it gives us the, excuse me, it gives us the actual formula. So I very well could write out the actual name under nomenclature rules, and you would have to determine what is lithium hydroxide. But for now, we have the information we need to go ahead and write out what we need to. So because it says complete and balance, I need to make sure that phases are included. And I know that these are aqueous because it tells me that these are a solution. Okay, the only liquid we have is water. Everything else that's a solution would be considered to be aqueous. Now, in an acid-base reaction, the hardest part is going to be predicting who is forming what. So I'm going to write this in black because I'm going to write over them in color to show you where the different reactant pieces are going. Okay. So we said earlier that an acid-base reaction or neutralization reaction always will form a salt and water. Okay. So fortunately for us, we know that the formula of water is H2O. So that's a constant. So I'm going to go ahead and write out my H2O because that's the part that I know. The part that I may not know is, well, what's the salt? Is that it's not NaCl because I don't have sodium in here, and I do have a chlorine, but it's in a polyatomic group. So let's determine where the water is coming from so that we can determine what's left over. So when I have my O, let's do a bright color, my oxygen, that's going to come from the oxygen in my base. And then one of the hydrogen, so I'm only going to color half, comes from that hydroxide group. The other hydrogen comes from my acid. So acids are proton donors, bases are OH donors, or we can think of them as being OH acceptors, I guess. So now the rest of it. So now I have lithium, and okay, so this is my salt. My metal plus my polyatomic gives me an ionic compound, which tends to be salt. Now if I want to see if they're balanced, I just need to total up the left and the right. So I have 2 hydrogens. I have 1 plus 4 oxygens. I have 1 lithium and 1 chlorine. So everything balances out. I don't need any subscripts. The hardest part of this problem usually is identifying the products. But if you can remember that water is always going to be a product, and the proton always comes from the acid, and the OH always comes from the base, all that's left over is the other parts that are with that proton or with that OH group. Okay, so practice, and then you have opportunity for CP points. The last thing is redox reactions. Okay, so we start off with redox reactions this semester. We really just briefly introduce them, and then we spend pretty much a whole chapter on them in the second semester. And so for right now, the only things that we're concerned about are determining who's oxidized and reduced, looking at the change in oxidation state, and then identifying the oxidizing and reducing agents, which actually is a lot more than it seems. Okay, so in this case, I'm going to make this a little bit bigger, work on the first problem, and then I'm going to save the second problem. And if nobody figures it out, that's fine. But I'm going to give y'all CP opportunities for this problem as well. So starting off with the first one, I would always identify oxidation state first, because that will allow us to kind of figure out the other two. So magnesium is going from 0 because there's no charge. When you have it in its neutral state like this on the periodic table, it's neutral. The same thing must be true about nickel. So they have a 0 charge. Now, one of the rules we said about halogens is that they are going to have a +1 charge. a 1 minus charge. So in this case, I have 1 minus and 1 minus. Now, because I have two 1 minus charges, that means that my X must be equal to 2 plus. So in this case, my nickel and my magnesium, which I might have already predicted because of magnesium being in the second row, the 2A, but nickel's a transition metal. I didn't really have a rule to predict that. So they're both going to have a 2 plus charge. Okay, so now I know the magnesium is going from 0 to 2 plus, and nickel is going from 2 plus to 0. So now I have to think about what's happening with the electrons, because redox reactions are electrons being transferred. And there's a really easy mnemonic that I've used to remember this. There are different ones. If you've learned a different one, use the one you know. But in general, oxidation is loss of electrons. Reduction is gain of electrons. Okay, so we need to, even though there are no electrons written in here, we need to determine where the electrons are in order to determine, are they being lost or are they being gained. So if I have a magnesium with a neutral charge on the left and a magnesium with a 2 plus charge on the right, I need my charges to equal each other, just like I did with the oxidation states up here. So where should I add electrons to balance out this right here? If I add 2 electrons to the left, I put 2 negative charges on the left with my 0, and that's like saying 2 minus equals 2 plus. And we know that that's not true. That can't be true from algebra, okay? We know that in order for that statement to be true, excuse me, that 0 must equal 0, or 2 plus must equal 2 plus. So if I add the electrons to the right, all of a sudden now I have 0 equals 2 minus 2, which equals 0, because each of these electrons is like a -1 charge. So this is true. So in this case, my electrons are on the right-hand side. And this is half of my reaction. Okay? Now, because the magnesium is giving up these 2 electrons, there must be somebody out there to accept those 2 electrons, and that is nickel 2 plus. So nickel 2 plus is gaining 2 electrons. It's gaining something negative. Therefore, it's becoming less positive, hence the 0 charge. And so the electrons are written on the left. And in this case, 2 minus plus 2 plus equals 0. Well, yes, that's true. Right? In order for them to cancel out, the 2 negative must be on the left with the 2 positive. So now I need to apply the oxidation reduction oil rig to my half reactions here in the center. So if oxidation is loss, that means that my magnesium to magnesium 2 plus is my oxidation. Now, because oxidation and reduction have to occur together, that means my nickel to my nickel 2 plus to my nickel neutral must be my reduction. Okay? So, change in oxidation state. Shown here. This is my oxidation. This is my reduction. Nickel 2 plus to 2 minus. Nickel 2 plus 2 electrons yields nickel solid. So I've answered both of these. And then now I need to identify the oxidizing and reducing agent. Now the thing that makes this confusing is we want to just pair up oxidation and reduction, but we can't do that because the oxidizing agent causes reduction and the reducing agent causes oxidation. So in this case, because that's true, my oxidizing agent is what causes reduction. And my Ra, my reducing agent, causes oxidation. Okay, now when we identify, let's not make this in this color. When we identify the agents, we are focused on reactants only. We are not focused on the products because they are not causing things to happen. They are being produced. The only thing that can cause a reaction is the reactants. Okay. So this particular topic is kind of a culmination of a couple of things we talked about today. The change in oxidation state, identifying redox reactions, and then oxidizing and reducing agents. Okay. So you have one whole problem to practice with, and if you are unsure, I really recommend Khan Academy or YouTube. There's Tyler DeWitt, Chemist Nate. Those are all going to be really great YouTube channels that would have more examples of this. But the only way to get good at this particular kind of question is to practice it because it's all about patterns. And so once you can practice it, you'll start to see some of the patterns arise. But if you only practice it today and with question 2 and with the 2 or 3 questions you get on sapling, you've actually only done it 5 times before you take the test. And that's really not a lot. If you think about anything you're good at, you've probably never just done it 5 times and been good at it. If you are, then maybe that's you're very skilled for that. But not many people are what I would say skilled to understand redox reactions. It's something we have to learn, just like any language, any new math technique. You have to practice it. So if you only do this 4 times, you may not be able to do this on a test. Okay. So you'll see here at the bottom, you do need to make sure you bring a calculator. I haven't really done the best about reminding y'all to bring those, but because we're going to start doing stoichiometry and y'all are going to be doing a lot of math, I want you to bring your calculator to class on Friday. Okay. Now I will be out of office all day today, and then I will be back tomorrow for lab. But if you email me, I'll be coming back from Dallas this afternoon, and I should be able to handle emails. But just remember, if you are Tuesday lab, your Thursday deadline for your last experiment report is tomorrow. So you have pretty much tomorrow to try to ask me questions. And then if you're in the Thursday lab, that this new report is due on Saturday. Okay, so we're going to stick with these new deadlines. It seems like it really worked quite well for you and gave me a little bit more breathing room on the turnaround time. Okay, our next test is coming up pretty quickly, so make sure that you are sorting through all this information to determine what you do and do not know. And then please come see me if I can do anything to help. And again, 5 problems to practice with on Friday.